Alrighty, good evening. Today we're going to be talking about Lewis structures. So what are Lewis structures? And these are different than Lewis dot diagrams. Lewis structures are what we use to pictographically show what a compound might look like. You can say pictograph or a diagram or a sketch. So it's kind of how we visually see what a compound might look like. It helps us to visualize how elements are bonding together. So how exactly, when you have CO2, how exactly are the carbon and oxygens bonding together. And it also helps us to visualize how two compounds might then react. So this would come in later, but if you're looking at how two compounds might react, looking at the Lewis structure of them kind of tells us how that might happen or where that reaction might take place. And Lewis structures tend to follow the guidelines of the octet rule, where elements try to obtain a full valence shell or a full octet. That means 8 electrons in the outermost energy level. And so that's the governing rule kind of for how we make Lewis structures. So at this point, I'd like you guys to take out a piece of paper and a pencil or a pen or your notebook or whatever and write down these steps. I'm going to teach you the steps to drawing Lewis structures, and you're going to need to have these written down somewhere so that you can reference them later when you're asked to draw Lewis structures yourself. So the first step is to count the total number of valence electrons for all atoms involved. So every atom that is involved in this, you need to count their total number of valence electrons and atom together. You then need to write the symbol for all the atoms in the compound, placing the atom that is listed first in the chemical formula or name in the center with all other atoms around it. So whenever we name or write chemical formula for compounds, we tend to list the centralized atom first. And this is not, number 2 is not always a steadfast rule. As with chemistry, remember, the only thing that is always true, there's always exceptions. Then connect the atoms with single bonds, so 1 electron shared from each atom. Once you've connected each atom to the centralized atom with a single bond, you're going to then complete the octets of all the atoms bound to that central atom. So for example, if it's a chlorine molecule or atom, that is connected to a centralized atom, the chlorine needs to have 6 valence electrons around its outside. It only forms 1 bond with 6 valence electrons. So you need to complete the octets of all the atoms bound to the central atom. Then any leftover electrons are placed around the central atom, making sure to have them paired. Lone electrons are not allowed. If there are not enough electrons to give the central atom an octet, try using double or triple bonds, making sure to maintain octets on all atoms involved in multiple bonds. So if you are going to make a double bond between oxygen and carbon, make sure that you appropriately count for the octet of oxygen as well as that of carbon. So you may need to take valence electrons away. So there are some exceptions to the octet rule, because there always are. Sometimes elements either do not obtain a full octet or will even exceed the octet rule. For example, boron. Boron actually doesn't obtain a full octet. Boron likes to be bound by 3 bonds when it reacts with something, or to have 6 electrons around it, so it doesn't obtain the full 8 through sharing. Through sharing, it has 6 electrons in its outer shell, but only 3 bonds, and that's okay. It's fully satisfied and energetically stable to just be boron trifluoride with no valence electrons around it. Nitrogen, kind of like boron, only likes to form 3 single bonds, but it also likes to have a lone pair of electrons there. So it completes its octet, but it does so by only bonding 3 times and keep maintaining a lone pair of electrons. So for example, ammonia has nitrogen with 3 bonds with that lone pair of electrons there. And that is how it is energetically stable and a neutral compound. Phosphorus likes to exceed the octet rule. It likes to have 5 bonds around it instead of 4, meaning that it has 10 electrons shared around in its outer shell. Again, this is how phosphorus is stable. And then sulfur actually likes to make 6 bonds. So typically it would make 4 bonds, maintaining that 8 bonds in its outer shell that are being shared, but sulfur actually likes to bind 6 times. So this would be sulfur hexafluoride and phosphorus pentachloride. So these are some 4 common exceptions to the octet rule. There are more, but these are 4 of them. For example, iodine will also exceed, will also not necessarily just form one bond, it'll actually form multiple bonds. But we'll get to that later. So here are some hints. Some very common, almost always situations. Remember, there's always exceptions, but these are some tending to be typical situations. Carbon will always, and remember when I say always, you have to take it with a grain of salt because there are always exceptions, but carbon will typically make 4 bonds. Oxygen will typically make 2 bonds and have 2 lone pairs of electrons. Sorry guys. 2 bonds with 2 lone pairs of electrons. So it maintains its octet, but it does so by having 2 lone pairs of electrons around it. Nitrogen will typically make 3 bonds and have 1 lone pair of electrons. I showed that to you last slide. Hydrogen usually only ever makes 1 bond. It only has the 1 electron to donate. And halogens will typically make 1 bond and have 3 lone pairs of electrons, or 6 valence electrons. However, sometimes they do not. Like I said, this is not always. You have to take always with a grain of salt. But those are some typical things that you can usually do to ensure that your Lewis structure comes out correct, is by following those 5 examples. So let's talk about an example. Let's talk about ammonia. Ammonia is kind of fun. Okay, so we have valence, let's count our valence electrons. That's our first step. So we have nitrogen, which has 5, and we have hydrogen, which has 1, but there are 3 hydrogens. So 1 times 3 is 3, which when you add 5 and 3 together, that means we have a total of 8 valence electrons that we need to account for in our bonding. So let's draw a picture. Let's draw nitrogen. That's the next thing we need to do, is draw out nitrogen. Nitrogen there with its 5 valence electrons. And then there are 3 hydrogens that we're going to interact. Okay? We are going to share these lone electrons on nitrogen. These 3, 1, 2, 3 electrons on nitrogen are going to share their electrons with 3 hydrogens and their single lone electrons. So 1, 2, 3. So they are going to form bonds. So whenever we make a bond, those electrons are being shared between the 2, or in this case 4 elements. All right. But we don't leave, when we draw Lewis structures, we don't leave in those dots. So we need to get rid of those electron dots and just show a single bond. These single bonds, like we said here, they have 2 electrons in them. So whenever you're counting your electrons, you can count a bond as 2 electrons. But we don't actually draw the dots in. That's not proper Lewis structure notation. So we have to get rid of them. So here, let's count our valence electrons. We have 2, 4, 6, and we left those lone pairs on nitrogen for 8. So 3 bonds, 6 electrons used, which means that we have 2 valence electrons remaining, and those valence electrons are placed, or left in this case, on nitrogen. Okay? Let's talk about a multiple bond example. So let's look at dicarbon dihydride. So we've got 2 carbons and 2 hydrogens. So let's count up our valence electrons. Carbon has 4, but there are 2 of them, so there's 8 electrons there, and hydrogen has 1, there are 2 of them, so there's 2 there. For the total, for the total valence electrons, then you have 8 plus 2, which is 10 valence electrons we need to take in account for. So let's draw our carbon atoms, our carbon atoms there with their 4 valence electrons each, and then we have 2 hydrogens. So here we're going to form those single bonds in between all atoms involved. So carbon is going to bond to this hydrogen, and this carbon are going to bond together. This hydrogen and this carbon will bond together, and then the 2 carbons will bond together as well. And remember, whenever we make those bonds, we have to get rid of our electrons. Sorry, we're going to do that next step. So we've made single bonds. This octet is already satisfied. So now we have to take care of these extra valence electrons, because right now carbon has 2, 4, 5, 6, and this carbon has 2, 4, 5, 6 electrons. It does not have 8 electrons in its valence shell. So in order to satisfy carbon's octet, it's going to need to share its electrons with each other. So they're going to form bonds there as well. So now this carbon has 2, 4, 6, 8 electrons in its valence shell. This carbon has 2, 4, 6, 8 electrons in its outer shell, and hydrogen is satisfied with its 2. Okay, whenever we draw bonds, we get rid of our electrons, and I'm going to make these 2 really long bonds shorter. So then we have 2, 4, 6, 8, 10 electrons utilized in making 1, 2, 3, 4, 5 bonds, one of them being a triple bond. So the bonds that we made were 5, which is 10 electrons, so there are no valence electrons remaining, meaning that carbon does not have any valence electrons. This holds steady with our carbon forming 4 bonds kind of rule or guideline that we follow. So now I want you to practice this. I would like you to try and make the following molecules. And when I say this, I mean do this, okay? Do it on a piece of paper, pause the video, and do it. I'd like you to pause the video and make carbon tetrahydride, or methane that we talked about in class. So pause the video and please draw this Lewis structure. And then when you're done, you can come back and check it. So I hope you've paused the video and drawn your Lewis structure. So now I'd like you to check it with me. Carbon tetrahydride should look like this, where carbon forms 1, 2, 3, 4 bonds, 1 bond with each hydrogen, and carbon then has 2, 4, 6, 8 electrons in its valence shell, and each of those hydrogens have 2 electrons, so all octets are satisfied. And carbon with its 4 valence electrons, and hydrogen with its 1 valence electron, but the 4 hydrogens, you have a total of 8 that you need to be concerned about, and we utilize 2, 4, 6, 8 electrons. Alright, next up, I'd like you to draw carbon dioxide. So please pause the video and draw this Lewis structure as well. Following the steps, if you need to, you can go back to the page where you have your steps, but you should have those written down. So I hope you've drawn carbon dioxide, and let's compare it to what I have here. So here I have carbon with 2 double bonds and oxygen with 2 double bonds with 2 lone pairs. So let's count how many valence electrons we should have. Carbon has 4, oxygen has 6, but there are 2 oxygens, so we should have a total of 12 from oxygen plus 4 from carbon, which is 16 electrons. Let's see if we utilize those. We have 2, 4, 6, 8, 10, 12, 14, 16 electrons. So we used all of our electrons, and 8 of them had to be utilized as valence electrons on oxygen, because oxygen likes to bond with 2 bonds and have 2 valence electrons. Alright, so that is what we're going to be working on tomorrow in class, where we're going to be practicing drawing a bunch of different Lewis diagrams or Lewis structures. And so please come prepared to do that. Have your list of instructions handy. If you need to go back and rewatch that part, you can, to write it down, because you will be doing this tomorrow in class. Alright, have a wonderful evening.